LPE is an additive manufacturing company we set up in 1991. We offer a full range of additive manufacturing solutions using industrial printers. We offer a wide range of plastics and metal materials. Our average lead time is 2 to 4 days. Almost 40% of our business is based on making direct parts with additive manufacturing or else tooling. The remaining 60% will be prototypes. We are ISO 13485 and ISO 9002 approved, and we're in the process of getting AS 9100. In the last 3 years, we've been actively involved in R&D with the NIAS Centre at Belfast, University of Ulster, the Northern Regional College, and the AIT in Athlone. So just a quick recap on terminology in relation to the field of rapid prototyping. From 1990 to 2000, people in the industry referred to it as rapid prototyping. And the reason why was predominantly it was used for prototyping. It wasn't actually used very much for production and for jigs and fixtures and tooling. So after about, I suppose again, the other thing as well I wanted to highlight is that in 1990 to 2000, all the technologies. Is the volume right on this thing? Can everybody hear there? That's it there. That's right better, yeah. Yeah. So back in 1990. All the technologies that you hear today in 3D printing were all in existence in 1990. So the very first technology was stereolithography. Today, stereolithography is one of the dominant technologies. SLS, selective laser sintering, which is a powder process, that was developed in the early 1990s, and that's still very much a dominant process today. You have FDM, which was the fused deposition modeling process, which is the process that led to the explosion of cheap 3D printers. And the reason that's when people hear 3D printing, they tend to think of FDM, and that's because the patents expired first on the FDM. And a lot of people get confused with 3D printing, but it was actually there in 1990. The other one is LOM. In Ireland here, we have the only additive manufacturer in Ireland is a company called EMCOR, and that's a paper lamination process. The LOM process was first in existence back in 1990 with a company called Helices. And then finally you have DMLS, which is direct metal laser sintering. And whilst a lot of people have only heard about metal sintering in the last couple of years, metal sintering was first on the market back in 1999. It was 10 years, probably about 9 years before, or sorry, 9 years after the other processes. So the other processes all have about 9 years head start on it. From the year 2000 to 2010, everybody switched to the terminology of additive manufacturing. And the reason for that was really that people started to use it for direct parts, and they started to use it for tooling. And that all came about from the result of process improvements. So the processes improved, the speed improved, and the material improved. So all of a sudden everything moved from rapid prototyping to additive manufacturing. And then from 2010 to 2015, the patents expired on the FDM process, and then all of a sudden there was an explosion of cheap printers, down as cheap as £500, and everybody was talking that everybody would have these in their houses. You know, kids would have them to make their own toys. So from 2010 to 2015, everybody referred to the industry as 3D printing. But then unfortunately everybody sort of realised that it wasn't going to explode and that it didn't live up to what everybody thought it was going to do. And now, around about 2015, at the end of 2015, there's been a big switch back to referring to the technology in the industry as additive manufacturing. And the real reason for that is because of metal manufacturing, because of metal 3D printing. That's what I'm going to talk about today. All the leading manufacturers, 3D Systems, Stratasys, they've all switched their focus. They've all come away from the consumer product, cheap 3D printers, and they're now all focused on the high-end industrial printers. So although there's polymers, ceramics, paper, commercial systems, on this particular talk I'm really only going to focus on metal additive manufacturing. Within the metal additive manufacturing there really is three types of metal additive manufacturing. And the main one I'm going to talk about today is the powdered bed fusion. So powdered bed fusion actually represents 85% of all the additive metal manufacturing in the world today. Of that, within powder bed fusion, you have two types. You've got laser melting and electronic beam melting, LM and EBM. Again, today I'm going to talk about just LM, the laser melting. In addition to the powder bed fusion metal processes, you also have what are called direct energy deposit systems. That's laser cladding and arc welding. And those are specifically aimed more at the oil and gas and the aerospace industry, where it's big, large parts, they're combination machines, and it's mostly used more in tool and repair. They all have specific applications. And the third bit for metal printing is it's an actual printing metal. It's not quite printing, it's a bit misleading. It's a binder, called the binder fusion process. So you don't get a metal part out direct, you get a metal part that's created with a binder in it. Then you got to take that component and you got to put it in an oven and you got to heat that. So it's a two-stage process. It does offer a bit of promise in terms of being able to offer cheap metal parts, but it is high shrinkage. The only company that is really doing anything significant in it is a company called X1. So up above, it's really all metal technologies. It's really all being driven by laser melting. If you look at the laser melting machines, that's really a quick summary there of the 6 main players. And those really are the 6 companies that if anybody's thinking about getting into laser melting, it's really one of those 6 you need to consider. And these guys represent 85%. So you can see it's been pretty much dominated by Germany. You have Concept Lasers, which is German, you have EOS, which is German, SLM Solutions, and then Realizer. Renishaw have their own machine now, but in actual fact the Renishaw machine was actually, Renishaw bought a company called MTT in Stone, and the guys in MTT had their machine developed by a German company. I think it might have been SLM Solutions. And although the Americans have bought 3D Systems, have bought a company called Finks. Finks is actually, I think it's a Finnish company. So all the machine development really on metal has all come from Europe. Just a quick overview of how the process works. So like all the 3D printing process, it's a layered process. So what you have is you have a platform that moves up and down, and you have powder that comes across. So one of the difficulties with the metal printing is that because it's metal, you've got reactive metals and non-reactive metals, so you have a very high chance, there's a very high risk of explosion. So you either have, for non-reactive metals, you have nitrogen, and for reactive systems, you've got argon. But the important thing is that the metal sintering, if you watch it, it's just like laser welding, laser melting. So you get like a lot of black oxidization. That black oxidization can fall onto the part. So it's really important that you have a really good air circulation system that takes the black oxidized parts away and doesn't infiltrate onto the existing part. That has a significant effect on the material properties that you're trying to achieve. It also has a laser system. The laser systems all go from about 100 watts up to 2 kilowatts. They have a focus and optic system that guides, that draws the part. They have scanners and they have the F-data lenses. So all these here are common to the laser liquid systems, the stereolithography and the selective laser sintering. But the one thing that is unique in the metal sintering is the recirculating gas system, which is critical. And it's one of the things that causes most of the problems. We just look at the main industries that are using metal AM. If you look to the left here, really, the dental and the jewellery were the 2 industries that really led the way in metal sintering. It wasn't so much that they chose to lead the way, it was just that their parts were small, so therefore they were quite cheap to build. And then it moved to the medical, and then it moved to the automotive, and then the mold and the aerospace. So I just want to throw up a couple of examples here. This is a company in Italy called Tsunami, who basically design spine and fusion implants. They totally redesigned every single one of their products. Every single product, if you go to their website, every single product designed by Tsunami is made on a laser melting machine. And this company now competes with the likes of Stryker and Johnson & Johnson, all the big companies. It's unbelievable what they've done. Another company here, although, is consumer electronics, a company called Ortofon. Again, redesigned one of their, one of their cartridges. They actually made that in titanium. Again, that's one of the things with metal sintering, is that sometimes it's cheaper to make something out of titanium compared to aluminium. We run stainless steel and aluminium, and sometimes we tell the customer it's cheaper for us to make this in stainless steel and aluminium, and they sort of look as if we've got two heads, but it is. This was the big application here that really shook up the industry, which was GE. GE spent 6 years redesigning that component. And that component replaces 20 components. It gave them a 3.25% reduction in weight. It increased the life of the product 2.5 times. They're now going to produce production volumes of 25 to 40,000, and by 2020 they'll have more than 100,000 parts. And the big thing about it was, at the end of that 5-year development program, what has happened now in the industry, at the end of last year, GE have gone out and they've bought Concept Solutions, is it? And they bought EBM Arcam. So GE, a lot of people think GE have got so afraid. This laser melting metal technology is so important to them. They're so afraid that they'll not be able to buy enough machines to support their products. They've gone out and actually bought the equipment manufacturers that paid 600 billion. So that's how confident they are that it's going to drive their business. Again, just if you're looking at metal sintering, the big thing is there's no point in just doing, if you look at metal sintering, you say, how much is this part to make, and compare it to how much it traditionally makes, then you're sort of missing the point. The whole thing about metal AM is you have to redesign it for metal AM. There's no point in just taking something you already have and thinking it's going to get a benefit. You might be lucky and it might be cheaper, but if it's very cheap to do using traditional methods, then metal's not going to be the solution. You need to add complexity to it, so you need to either take weight out of it or you need to combine parts. Those are the materials. There's a wide range of materials. The big advantage of laser melting is it doesn't matter what material you're interested in, you'll be able to get a powder for it and you'll be able to laser melt it. But the most common ones are stainless steel, cobalt chrome, aluminium and titanium. This is just a quick map I put together. It's sort of like an adoption map. So if you consider, this is where, as a company, we're producing test prototypes, but we're producing test units. We actually produce spacecraft parts that fly on satellites, and we produce parts for F1. And that's where we as a company are at the moment. In 3 to 10 years' time, we reckon that we'll be doing low volume production and high value added products like medical, automotive and aircraft parts. But for companies who are thinking of buying it, really, this is what you need to look at, is the speed. As the speed of the process improves, then more people are going to start to adapt the applications. I highlighted to you that in the early days it was the medical, the dental industry used it. That was because their parts were small and they could build them very quickly. Now we can build large parts quite quickly. If I think of stereolithography, when I first started out in stereolithography, a part that maybe took me 50 hours to build, today I can build it in 10. Metal sintering is going the same way. The speed is improving quite dramatically. At some point, the speed's going to get to the point where it's more cost effective to make it. So just quickly then, in summary, the technology is not going to replace CNC, it's not going to replace investment casting anytime soon, but it represents, in its present form, it is a game changer for certain products. There's no doubt about it. It really is a game changer for certain products. It brings with it the limitations of existing rapid prototyping and AM in terms of geometry, support issues, and thermal problems. But what differentiates this from the plastic processes is that it delivers material properties that are better than the metal investment casting, and the parts are 99.99% dense. And quite often we've had companies, we had a Formula One company come back to us and told us that the strength of the part was better than their investment casting, it was stronger. Material options are unlimited. The process is slow and consequently more expensive than plastic. To get an increase in speed requires larger lasers, and when you go to larger lasers, the part becomes coarser, and people think the surface finish isn't so good. So of his annotation. That's it. Thanks for listening.